This is a video for AQA Further Pure Mathematics, Calculus Section 3.3, Integrating using arc sine x. Well, we've already seen the results that the derivative of arc sine x is 1 over root 1 minus x squared, and that if we've got x over a, so arc sine x over a, then that is equal to 1 over root a squared minus x squared. So we're going to use these results to look at some integrals now, because obviously if these are the derivatives, then we can integrate and show that the integral therefore of 1 over the root of 1 minus x squared dx must be equal to arc sine x plus, of course, a constant. And similarly, the integral of 1 over the square root of a squared minus x squared with respect to x must be equal to arc sine x over a plus a constant. So that we have these two results that we can use for integrating expressions which look like those on the right hand side of this page. As an example of that, then, let's consider this expression here, in which we've got 1 over the square root of 4 minus x squared. So this is just our equation where we've got 1 over the square root of a squared minus x squared dx, where a is equal to 2. So as we know that our standard result says that the integral of this is equal to arc sine of x over a plus c, we can simply write the result down from our known result. So this here must be equal to arc sine of x over 2 plus constant of integration. So this shows that because we had an integral which was in the standard form, that we could simply write down the result. We could recognize that a was equal to 2, and therefore our solution must be arc sine x over 2 plus c. Well, here's a similar looking question, but this time the denominator is not in the form that we need. Remember that we want the square root of a squared minus x squared. But in this particular case, we've got a multiple of x squared. So we need to start by factorizing out 2 from that denominator, so that we get the square root of 2 multiplied by 9 over 2 minus x squared. So we can rewrite this integral as being equal to the integral of 1 over the square root of 2 multiplied by 9 over 2 minus x squared. So that's the square root going right over that bracket there. We can take that first root 2 outside the integral, so that this is then equal to 1 over square root of 2, the integral of 1 over the square root of, and then 9 over 2 minus x squared. Now this is now in standard form. Sorry, I forgot to write the dx on both of those integrals. This is now in the standard form here, where our value of a is equal to 3 over root 2. So here we've got a squared is equal to 9 over 2. And therefore a is equal to the square root of 9, which is 3, divided by the square root of 2. So we can now say that our standard result can be used So that we get the 1 over square root of 2 from outside the integral, arc sine, and we want x over a, so that gives us arc sine x multiplied by root 2 divided by 3. So x over a was equal to 3 over root 2, and of course we've then got plus the constant. So just to show you where that part of the sine came from, we've got that x divided by a, and a was equal to 3 over root 2. So that's equal to the square root of 2 multiplied by x, or x root 2, and divided by 3. It's important then when tackling this type of integral that we first of all consider the denominator and make sure that we write it in the standard form of a squared minus x squared. So on the bottom line there we've got the square root of a squared minus x squared, and that will require some factoring of the expression. But once you've done that, then the standard result can be used, that the integral of 1 over root a squared minus x squared is arc sine x over a. In summary then, this is a result that can be quoted, so you don't need to prove this every time, although some questions may ask you to go through the proof that of the derivative that we saw earlier. If the coefficient of x squared is not equal to 1, remember that you must factorize out that value to give us a denominator in the correct form. This is the end of this particular video. In the next one we'll be looking how we use integrating with arctangent of x.